Yeah, so thanks for allowing me to come and present at this forum. I'm going to be talking today about single pass subsurface ocean detection at Triton using principal components of magnetic induction measurements. So this work was actually funded by the Triton Discovery Mission Concept, which many of you may know or not, had a primary goal of subsurface ocean detection at a single pass at Triton. Many of you may know that this mission concept was not selected for further study, unfortunately, due to two Venus missions that got selected. But we're hoping that this work sets a stepping stone for some of the future possible missions to the outer planets, namely Neptune and Uranus. There's a lot of promise with a potential mission in the future with the release of the decadal survey. There's a lot of interest in that. So with that, let's get into it. So what is the evidence that oceans exist in the solar system? Why are we looking for other oceans? And the main reason why is because we've found oceans on other moons before. The most compelling evidence of subsurface oceans comes in the form of magnetometer measurements from Galileo. We see here the C3 Callisto Pass and the E4 Europa Pass. These are the magnetic field signatures as a function of time along the flyby, where 0 indicates the time at closest approach. And you'll see this deviation from linearity, this little blip in the middle of the screen in each one of the components, as well as the magnitude in the bottom plot. And this is associated with the magnetic induction signal from the subsurface ocean beneath. A magnetic induction response from a subsurface ocean was first proposed by Marty Tuvelson and Krishan Khurana and able to explain this data. And they were able to show that the magnetic signature of these moons are synchronized to Jupiter's rotation period. And what this means is that as Jupiter rotates and you pass the moon at a different time, essentially you have a different orientation of the dipole field that's induced. So I just quickly flipped back and forth. I'll do it again just to show the changes. Now you see these C9 pass of Callisto and the E14 pass of Europa. So this exciting result forms the basis of the Europa, Clipper, and JUICE missions, which have goals of characterization over the course of many flybys. So why is Triton thought to be an ocean world? We all know that Voyager 2 was Triton's only visitor and Neptune's only visitor, but it didn't fly close enough to the moon to determine whether or not there was an induced magnetic field. The induced dipolar field is inversely proportional to the distance cubed away from the moon. So it's going to get pretty close to be able to sense this phenomenon if it's present. But there's two reasons why we think that Triton might be an ocean world. One, it's thought to have sufficient heating to support a liquid ocean. It's a captured Kuiper belt object based upon its orbit and composition, but its high inclination results in significant obliquity, which is able to provide sufficient heating to maintain a liquid internal ocean. It also has diverse geological surface features consistent with oceans. It's got smooth plains and this cantaloupe terrain you can see here. This indicates some resurfacing from within via cryovolcanic or tectonic nature. And it's also, Voyager 2 also observed active plumes on the southern hemisphere. So Triton comes with a lot of complications for potential ocean detection. And one is that, and this could be any moon in the solar system, the obscuring effect of an internal self-sustaining dynamo like you see at Ganymede. We cannot rule this out, but it's thermodynamically not likely at Triton because of its small size. It's got a really intense ionosphere. And by that, it's really conductive. So as I'll explain, magnetic induction is only facilitated when you have a conductive layer internal to the body, like a salty ocean. But if you have a strong conductive ionosphere, that will also induce a magnetic field that can obscure the signal from below the ocean. Plasma interaction fields from magnetospheric currents. I don't have much time to talk about it in this particular talk due to the time limitations, but we were able to determine that these currents are minimal at the particular orbit of Triton. There's also uncertainty of Neptune's magnetic phase. depending upon when we encounter this, we have to be robust against multiple phases of Neptune, because the multiple waves that come in at different frequencies actually can add destructively to minimize the effect of the magnetic induction signal. I'll try to explain that in a little bit. And also low amplitude driving waves in the presence of various noise sources. So we actually developed a new methodology to handle this, demonstrated through Monte Carlo simulations. So this new ocean detection methodology actually received a major strength in our CSR, our Triton CSR. It says the ocean detection data analysis approach is novel, well-detailed, and represents a potentially powerful approach for establishing the presence or absence of a subsurface ocean. So what we do is we actually model tens of thousands of different interior models with an ionosphere and without an ionosphere. And these different models contain different ocean thicknesses, conductivity, depth, and ionospheric conductance. And we actually use principal component analysis to assess the classification of the measurement. And this takes advantage of all the energy in the magnetometer channels. And this leads to a concept called scaled magnetic moments. And this results in a separation of these two model classes, ionosphere only and ionosphere plus ocean models. This is applicable for single and multi-pass encounters, and is also used for ocean characterization. So typically in a longer talk, I'd be able to talk a little bit about magnetic induction, but due to time limitations, this is all we have. So magnetic induction is based upon a principle called, obviously, Faraday's law of magnetic induction. And this basically states anytime you have a time-varying magnetic field, dB/dt, is equal to the curl of the electric field. So there's always going to be an electric field when you have a time-varying magnetic field. So this will drive currents within a conductive body if present, and will induce a secondary magnetic field opposing the driving field. So the key ingredient of magnetic induction is you need a time-varying external magnetic field. And for Triton, it comes from Neptune. And we observed the multiple magnetic waves at the orbit of Triton. The one is due to the tilt in Neptune's magnetic axis with respect to its spin axis. It's 47 degrees. And because when Neptune rotates, Triton actually experiences different magnetic fields at the 14-hour synodic period it takes for Neptune to rotate. And additionally, you see Triton's highly inclined orbit here. It's almost near circular, but its high inclination allows Triton to see different magnetic latitudes, which allows it to see a sinusoidal wave at the orbital period of 141-hour wave. So in this previous plot, which you can see Triton or Triton orbiting here along this dotted line, and this green arrow, this vector, is essentially the direction of the arrow of the magnetic field where it's pointing. And if I were to plot the Bx, By, and Bz components as a function of time, we get something that looks like in the upper right. You can see the slow or the faster 14-hour period, the synodic, and also the 141-hour orbital period. Now, if we take the Fourier transform of this, what we see is we not only have these two fundamental periods, but we have the beats and harmonics of the two fundamentals. Now, magnetic induction is the product of these driving waves times what we call the amplitude response function. And the amplitude response, or the complex response function, is composed of a relative amplitude parameter, this AK, where A is the amplitude and K represents the specific frequency that we're talking about. And phi K is a phase delay parameter. And this determines how delayed the response is from the driving wave. So this basic equation shows the magnetic moment for an individual wave at frequency K. And the scale factor AK and phase delay phi K are dictated by the ocean thickness, conductivity, and the depth of the interior layers. And again, for every frequency, we have a different magnetic moment. But the total magnetic moment is actually the sum of all these discrete moments together. So real quick, I know this is could be quite complicated, so I like to have a lot of animated visuals to help explain what this phenomenon is. And what we see on the left, we see Triton, and you can see this red vector emanating from the center. This is the total magnetic moment that I was referring to, and this rotates as the same period as Neptune rotates, so it's synchronized. The cyan lines emanating from it are the dipole field lines associated with this induced magnetic moment. So the dipole field lines are actually rotating with this magnetic moment as a function of time. But this is not exactly what we measure. We measure what's on the right. And on the right, we have the summation of the induced dipole magnetic field plus Neptune's magnetic field. And you see that red line that just streaked across the screen. That was the trajectory of the Triton concept. What on the right is what we're trying to measure, is what we actually measure, and what we're trying to detect is actually this the magnetic moment. That gives us the information of the interior properties of the moon that we're looking at. So when we get a measurement, what is the best way to infer that measurement to an interior properties of that particular moon? Now, when we use this model here on the left, we have a non-conductive mantle, a conductive ocean, a non-conductive ice shell, and a conductive ionosphere of varying layers of thickness with different conductivities. We do this because it allows us to tailor any conductivity gradients in the ionosphere that may be present. And again, I emphasize the importance of simulating the effect of the ionosphere, because this will also induce a magnetic moment because it's highly conductive. So our ocean space, what we do, as I mentioned before, we model tens of thousands of oceans. But here is our ocean space in the bottom. Every one of these dots represents a single model of ocean thickness from 10 to 310 kilometers with conductivity of 0.1 to 30 Siemens per meter. The blue dots are the oceans that are most likely. The gray dots are the least likely oceans, but are carried along in the analysis to show where the method breaks down. And then the green dot represents our least favorable likely ocean, and this ocean helps define our margin. So if we plot the, so what we do is we not only do we have these ocean models, but we convolve each one of these ocean models with 50 different ionosphere only models. And this gives us our, our 13,000 different models used in this study. And if we plot these models, we forward model them in the complex response plane for the synodic frequency on this top plot right here. We can see separability of the two model classes. And the model classes are defined by the blue region. Those are our likely ocean, and those are likely ocean plus ionosphere. And the magenta dots represent our ionosphere only model. So no matter what, we'd expect to see an induction signal there, but looking at this space shows us there's separability between the two spaces when there's an ocean present. And we want separability because that's the determining factor of whether or not we can determine whether there's an ocean there or not. So this top plot is represents the synodic frequency. And what you'll notice is that there's great separability to the left, but as soon as you go to the right, there's a convergence of the oceans and the ionospheres. And so in this region, we can't really definitively identify whether or not there's an ocean present or not because of this overlap. So this forces us to look at the orbital frequency, the 141-hour period, which is shown below. And as you can see here, there's great separability between all the ocean plus ionosphere models from the ionosphere only models. So if we take this one step further, we can forward model the total magnetic moment using this complex response function multiplied by the driving waves. And we get something that looks very similar. Again, great separability with great magnetic separation. And this magnetic separation defines the ocean model and the ionosphere that it was convolved with. So we want to maximize this separation as much as possible. So I talked about the magnetic moment. That's not what we measure along the trajectory with the magnetometer. we actually measured the induced dipole, and that's related to this equation up here. And the Bx, By, Bz components of the magnetic dipole are related to the magnetic moments, the Mx, My, and Z component, by a 3x3 dipolar matrix. And essentially, this is what the, if you look at the bottom three plots, this is essentially what all those models look like on top of each other. The Bx channel, the By channel, and the Bz channel. I know they're plotted on top of each other, but even if you had an isolated ocean plus ionosphere model plus an ionosphere model, it'd be very hard to distinguish which ones are which based upon the line shape. So there's no real concept of magnetic separation in this domain. So what we do is we shove it all into PCA. And because this is a forum on machine learning, I don't think I really have to go into the details of PCA. But the gist of it is that it's basically a way to, it's an eigenvalue decomposition method in which it extracts the most useful principal components from each one of these data sets. So what we do is we take all these models, we stack them, we stack the Bx and By and Bz components as shown here on the screen, and then we align them in a large matrix. We perform an eigenvalue decomposition, extract the eigenvectors as shown below, and these are the top three and shown below. And then we can project those forward model data into a classification space shown here on the right. So when we actually get our noisy measurement, this orange trace you can see here superimposed on the left, we can use those eigenvectors to project that into this classification space. And depending upon where this ball and model lands, it tells us whether or not we have an ocean or an ionosphere. Okay, so one of the things that that we have to be resilient against is the uncertainty in Neptune's magnetic phase. So here are plotted in 2D space and 3D space, all of the forward models that I've shown on the previous slides as a function of time for different Neptune magnetic phases. So these things actually rotate. And if I were to plot the separation distance between the ionosphere only models, the magenta dots, to every single one of the ocean models, we get this plot over to the right. And this shows the magnetic separation as a function of height integrated conductivity of the ionosphere. So we have greater separation at the low height integrated conductivity of the ionosphere because it's least conductive. So the 14-hour wave can actually participate more in the magnetic induction. But as soon as we go further away, we're more reliant on using the 141-hour wave, which has a better chance of penetrating the ionosphere. However, it's a lower amplitude wave, so we have less signal to work with. Similarly, we do the same thing in PCA, and this is what the data set looks like. As you know, PCA automatically organizes the axes based upon the variability of the data. So the greatest variance is along the x-axis, the second is along the y, and we can see that here in this data set in the left plot. PC3 has a lot of information in it too and provides great separability for every single magnetic phase of Neptune. And sure enough, when we plot the magnetic separation, you get an enhancement of this separation. But again, I love showing this plot because it's kind of ironically looks like an ocean wave. Okay, so here are some of the ocean detection results. We actually ran Monte Carlo simulations, 1,000 flybys for each one of the 13,000 different models, which includes instrument noise, spacecraft position, attitude, timing uncertainties, and interior model-based uncertainties. And we figured that we determined that this contributed about a 1 nanotesla noise limit, and this is a 3 sigma noise limit. So using this noise limit, we can actually determine how well we can detect particular oceans within our space. The 4 plots here show the parameter space, ocean thickness versus ocean conductivity, for 4 different ionosphere height integrated conductivities. The left plot shows 10,000 Siemens, then 30,000 Siemens, and 50,000 Siemens, and then 80,000 Siemens. And as you can see, the darker shades of blue show greater separation and therefore better discernibility between ionosphere-only models and ocean plus ionosphere models. So ideally, if we went there, we'd like to have, we'd like to see the ionosphere with low conductivity. However, it's more like the second column, the 30,000 Siemens column, in which Voyager 2 had made those measurements. But as you can see, the further you go to the right, the more similar they look, and that's because the 14-hour wave cannot penetrate the ionosphere. And this is for the magnetic phase of 0 degrees. We also did this for 120 degrees, and this actually coincidentally is the worst case scenario. And I talked about these two different waves, the 14-hour and the 141-hour wave, and these magnetic moments add. And it turns out at this particular phase, these magnetic moments actually nearly oppose each other and destructively add. And therefore, you're left with a little signal to work with for the classification space. So this is not an ideal condition. However, I do want to point out that if you remember correctly, our likely ocean space is actually contained in this black dotted line here. So even in the worst case scenario of the height integrated conductivity of 30,000 Siemens, we see that there's still a margin of 2 nanoteslas, at least 2 nanoteslas for the worst case ocean. So we still think we can detect all oceans that are likely, even in this worst case ionosphere and worst case magnetic phase. And just for completeness, we show the 240-degree magnetic phase to complete the circle here. And this looks really favorable as well, as indicated by the darker blue regions that we see on the screen. Okay, so this is mainly a talk about single pass detection, but I do just want to throw out real quick while I have a minute or two left, that the method is also very applicable to multiple encounters. Because we had a lot of trajectories to work with, because we wanted to optimize a single one, we actually have an abundance of data trajectories that we carefully stitched together. So here we have 5 different trajectories at different argument of latitudes. And sure enough, when we stitch this together, all these signals together, we throw them all into PCA, it does its processing, and we get significant improvement the more flybys we add. So the bottom, the magenta trace shows our least favorable likely ocean as a function of height integrated conductivity. And this is an argument of latitude of 90 degrees. But the top blue plot represents the concatenation of all the 5 different flybys at 90, 45, 0, minus 45, and minus 90 argument of latitudes. And as you can see, the magnetic field separation between the ionosphere only models and the ionosphere plus ocean model separates. So this gives us more margin to be able to discern or even characterize what these oceans are. And just to give an example of this, so these plots are basically shown are a similar form in the 2 slides that I showed previously for detection. But here, what we do is we show the contours, 3 different contours of 1 nanotesla contour defined by the blue. The cyan represents the 0.5 nanotesla contour, and the 0.1 nanotesla represents the or is represented by the red contour. And because the Monte Carlo that we performed, the 1 nanotesla contour is the one we want to focus our eyes on, because that's more of a practical limit of our noise in this experiment. Then we also have 3 different oceans shown on each one of these panels. Ocean 1 has a 6.5 Siemens per meter conductivity, 70 kilometer depth. Ocean 2 is a dashed line. This is a 4.5 Siemens per meter conductivity at 170 kilometer depth. And then ocean 3 is the dotted lines. This is a 2 Siemens per meter conductivity with a 250 kilometer depth. And this top row shows what we get for 1 flyby, the contours for 1 flyby. And as you can see, for the 10,000 Siemens case for the ionosphere, we can put some constraints on the particular oceans. But as soon as we go to an ionosphere height integrated conductivity of above 30, things get really complicated and not discernible. So detection's possible, but not much characterization. So when we stack 3 flybys together, we get a lot more tightening up of these particular contours. And this allows us to put better constraints on our oceans. And then once again, we go to 5 flybys and even tighter constraints can be performed. So even with a really, even with the worst case height integrated conductivity of the ionosphere of 80,000 Siemens, which is really a lot larger than what we think is there, we still think some form of characterization is possible. But at 10,000 Siemens, as you can see, the really tightness of these contours allows us to characterize the ocean pretty well with a handful of flybys. So that's all I have for today. I know it was a lot, but I'm glad to take any questions, and I'll just leave you here with an animation that we did of the final flyby. There comes Triton right there, flying by Triton. So with that, I'll take any questions if you guys have them.